Alright, so this is kind of like an application question of a real life scenario where you have the mean and the standard deviation and you're trying to decide like, which one's going to be the right one or the right quantity. So let's take a look at what we got. So we have a manufacturer that makes popcorn and potato chips. The average weight of what you're supposed to be. So our standard, what we're supposed to be. Okay, so when it goes down the line, what we're supposed to have is a mean equal to 3.07 and a standard deviation of 0.03 ounces. And the average weight of a bag of potato chips is supposed to be, alright, and so, I'm sorry, that was popcorn. So let's put popcorn, and then let's put chips. And so the standard for chips, the mean is equal to 5.07 and the standard deviation is 0.04. So a factory worker randomly selects a bag of popcorn from an assembly line that has a weight of 3.06. So the sample that I pulled, the sample of popcorn is equal to 3.06. And then the worker randomly selects a bag of potato chips from assembly line, and the weight is, so the sample weight, the X value of the chips is equal to 5.03. So the question is, which description closely matches the findings of the assembly line? So when we compare this, when we think about it like on this normal distribution curve, and we just like lay it out to kind of see, remember that your mean is right smack in the middle. So we have a mean of 3.06, and then we have and kind of just change colors so we can kind of compare the two, 5.03. And if we go up one standard deviation, so we say clear 3.06 plus our standard deviation is 0.03. So one standard deviation would be 3.09. Oops, wrong color. Let's clear that. Let's get black so things stay consistent. So that would be 3.09. If we did the 5.03 and we added on the 0.04, so plus 0.04, so we get 5.07. So when we compare the two, it's not like you can tell, oh, well, that one's 3/100ths away and that one's 4/100ths away, but the data values are larger, so it's kind of hard to like say which one is better. And that's where the z-score comes into play. So our z-score is the standardized score that allows us to compare and to give an idea of relativity. So we can compare two different sets to be able to give an idea of which one is closer to the mean. So we calculate the z-score for each one, and so we do the z-score for the popcorn, and our x was 3.06 minus our mean, which is 3.07, divided by 0.03. We pull out our calculator. So we got 3.06, oops, 3.06 minus 3.07, and we divide that by 0.03, and we find out that we have a z-score. I was sorry about that. I was just kind of thinking through there. I had the numbers written down wrong, didn't I? Well, that's not very good there, Fix, because the mean is 3.07. So please forgive me. Instead of recording this, let me just make a quick correction right here. That the mean for this guy was 3.07. I put down 3.06, and so if we added on one standard deviation, that would take me up to 3.10. And then if I did the same thing, I made the same mistake there. My mean right there instead of that would be 5.07. If I add on 0.04, that would take me up to 5.11. So same idea. This doesn't really help us because here we can see it's 3/10 difference or 3/100ths, and here we can see it's 4/100ths. but it doesn't help us. And the point was is showing you there is that, yeah, that's great, and we can look at it, but we can't really tell which one's better. We actually have to find the z-score. So let's finish up finding that z-score. We take that, we divide it out, we get negative 0.33 repeating. If we go find the z-score for the popcorn, for the chips, the z-score for the chips would be, our data value is 5.07. Come on now, Fix. How about no more mistakes on this question? My z-score is, or my x-score, is 5.03 minus my mean, which is 5.07, divided by my standard deviation, which is 0.04. So 5.03 minus 5.07, divide that by 4, and we come out with a z-score of negative 0.01. So here's what I want you to see, is that when we take the absolute value, when we compare those two z-scores, when we take the z-score of the popcorn and we see that it's negative 0.33 repeating, and then we take the z-score of the chips and we see that it's negative 0.01. Well, what we have to do here is we have to realize if we take the absolute value of either one of those, so if we absolute value them, just to kind of get an idea, what we're going to see is that we get 0.01, which is less than 0.333. And that means that 0.01 is closer to the mean, which means I have less variation, less discrepancy from the mean. So our best situation is going to be the chips. So let's read these and see. The popcorn bag assembly line is closer to the specifications given because its z-score is closer to the standard score. No, that's not true. The popcorn is further away because the popcorn is 0.33, so that one's out. The popcorn bag assembly line is closer to the specification given because its z-score is further. No, that's the opposite. Those two statements are opposite. If you're closer and then further, those are opposites. You can't be close and far away at the same time. The potato chip bag assembly is a line closer to the specifications given in its z-score and is closer to the standard mean. That's our guy right there. So that's what our z-score does for us, is it allows us to determine how close or relative we are to our mean. It allows us then to establish which data score is better than the other data score.